Okay. Good morning, everyone. So like I just said to Victor, a 2-minute, not interlude, prelude, I guess, on this work. This is some of the work I referred to yesterday when I said I was going to share you new results in that talk, and then I didn't get to it. So this is from Era 5. My postdoc with Michaela Hadchonlo did this work. The x-axis in both cases is wave number, frequency y-axis. And this is co-spectra, so V times meridional wind times moist-static energy at 850 hectopascal. And this is a signed quantity. So blue means southward, red means northward. The left panel is north of the climatological ITCZ, so from 5 to 20 north. And then the right panel is from 5 north to 20 south, so just south of the mean ITCZ. And the first order picture is sort of what I was mentioning to Victor just now, this very, very consistent north of the ITCZ, all of the space is going north, and south of the ITCZ, all of the space is going south. There is some hint of it being more in the sort of TD Western type, right? That's standing out more than other regions. But yeah, all of the eddies of all scales seem to be working to give you this down gradient flux of moisture and intern energy. So we're still trying to wrap our heads around that. Okay, so let's now turn to the actual talk about the Hadley cells. All right, so the Hadley cells are actually my first love, as much as I've fallen for the Indian monsoon and the ITCZ. The time mean, zonal mean Hadley cells, understanding them is sort of like the most fundamental core intellectual base for me. So I'm really excited to share this result with you. We'll focus more on dynamics, flows of momentum, than we will about energetics or moisture or anything like that. I'll also focus almost exclusively on the time mean and zonal mean, right? And that I want to flag as, I think of that as of being an intrinsic good, right? By which I mean, it's nice when we can then take our zonal mean arguments and apply them to zonally confined sectors, potentially like the monsoons. But I think understanding Earth's general circulation, the time mean, zonal mean circulation, is itself a fascinating and beautiful topic worth our attention, irrespective of what we learn about any local region from it. Okay, and then last preamble is I'll also focus primarily on the extent of the Hadley cells, so how far they move, extend north and south, and how that gets modulated, especially on the seasonal timescale. And Marty, coming right after me, is going to focus much more on the strength of the overturning. Okay, so having cleared my throat with all that, let's get into it. Okay, so got a little bit ahead of myself here. The time mean, zonal mean circulation, we call the general circulation. And we see here kind of like your standard textbook schematic of that. And there's much that is useful here. So we have in the tropics, these overturning Hadley cells. That's what we're going to be talking about. We have the surface easterlies in the tropics and westerlies in the extratropics at the surface. All of that is good. We have our ITC just north of the equator. And then in addition, which in some sense is true, we have, of course, your oppositely oriented Ferrel cells in the mid-latitudes, and then this polar cell thing, this 3-cell structure. In terms of the Eulerian mean stream function, that is correct, right? Those are all there. But what I want to emphasize is that I think for intuition about the tropics and the extratropics, I think a much more useful schematic is more like the following. So for the tropics in the YZ plane, indeed, we have the Hadley cells, right? That time mean quasi-steady overturning circulation is sort of, to first approximation, the predominant feature. But in the extratropics, what's much more central than the feral cells is we switch there to not Y versus Z, but it's actually more helpful to think about Y versus X. Take a horizontal view from top down. Is just all sorts of craziness, much of it organized into these large-scale Rossby waves, many generated by baroclinic instability, and a very nice descriptive term for this regime, the extratropical regime, is macro turbulence, right? So again, in terms of the Eulerian mean meridional overturning, we have Hadley feral polar cells. In terms of your intuition for the circulation in the different regimes, I think you much better thinking about a Hadley cell plus all of the myriad waves that Victor and others have talked about. I don't want to give those too short of shrift. And then this eddying, highly rotating macro turbulent extratropics. And given that, this edge, this poleward descending edge of the Hadley cells marks sort of a transition, right, between those two regimes. And thinking in those terms, we're going to think in those terms about the descending edges sort of again and again in this talk. The time mean, just to clarify, the climatology, that includes the climatological seasonal cycle, right? And not just the annual mean. But let's start with the annual mean. And in fact, let's start with a very naive question, which is, why is there any general circulation at all? Right? You guys learned earlier in the week about radiative convective equilibrium, this local balance between your radiative and convective processes. Why don't we just have that everywhere in the tropics, right? Why is there a Hadley cell in the first place? There are plenty of scenarios where that can be what emerges, right? So in an example, you know, of course I go to something by Isaac, but in a doubly periodic domain, uniformly insulated and uniform SSTs and other boundary conditions, we have just this sort of popcorn convection, right? It's moving around, it's coming and going, the different towers, but there is no mean circulation that emerges, right? This is in a climate model, so with parameterized convection, et cetera. Yeah. You can also get that in a cloud resolving model, right? So where you're not using resolve for, where you are resolving your convection. This is from Alison Wing's work, OLR here, and this is another example of this sort of disorganized popcorn convection in an RCE state. And it doesn't have to be doubly periodic on the sphere, right? Like our actual geometry. If, again, the forcings and the lower boundaries are all themselves uniform, then you get, and it's non-rotating, you get this popcorn convection RCE state all over again, over the whole domain. In all of those cases, you have an upward transport of heat and moisture compared to your radiative equilibrium state, right? Convection is bringing moisture and heat from the moist surface where the insulation is being absorbed and bringing it up high into the troposphere. Right, and this picture is the first sort of single column model, really compelling version of this applied to the climate change problem by Suki Manabe is what led to our field's first ever Nobel Prize, right? Just a few years ago now. So again, we have at any given time, there's lots of flow happening in 3 dimensions, but time mean, domain mean, not even domain mean, time mean at every individual location, the flow is exactly 0, right? There is no general circulation. Okay, so let's now go from that to having Hadley cells, or we're trying to. What's the recipe for that? So still, let's keep the lower boundary uniform. Let's go to an aquaplanet setting. So no continents, no diurnal cycle, no seasonal cycle. In that case, but otherwise Earth-like, there are 2 key ways that the system differs from those previous RCE scenarios. Does any of the students or attendees want to take a stab at 1 or 2 of those? The standoff. Not doubly periodic? Well, it is in the sense that it's a sphere, right? But I like it. All right, well, the key is that the incoming solar radiation, the insolation, is not uniform, right? And second, the planet is rotating, right? Once every day, once every 24 hours about its axis. Those are the 2 ingredients that fundamentally drive the whole general circulation, right? Okay, so the sunlight is coming pretty much in a all parallel rays because we're so far from the sun. And that incident on a sphere where the equator is normal to those rays, but the poles are nearly parallel to them, that results in the watts per meter squared of surface area being highest at the equator and lowest at the poles. And there's no zonal variation in that, right? That's true at all longitudes. So that's the non-uniform insolation part. Let's pretend now, though, that at each latitude sustains this RCE state. So the equator is convecting and is radiated and is convecting, but it's going to come to local equilibrium. 1 degree north and south are going to come to their own equilibrium, 2 degrees, et cetera, et cetera. So the whole domain, we're going to say latitude by latitude. What if each latitude came into RCE? What would the state look like? What, of course, happens in that case is that you end up with a non-zero, a non-uniform temperature, right? You're going to be warmest at the equator, coolest at the poles. And we can actually do that calculation numerically. So in the green curve here as a function of latitude is simulations where we've just concatenated a bunch of single column model RCE simulations, each one's corresponding to the insolation at that particular latitude, right? And you would get, in terms of deviations from the global mean of that, you would get a mean temperature profile that looks like that, right? Okay. So that's one ingredient. We have non-zero and decreasing poleward temperature gradients. Now we bring in the rotation. The planet is, it may not seem like it, one rotation per day, but given the other scales in the system, that rotation rate makes us a rapidly rotating planet, right? We have to keep in mind, though, for the horizontal plane, where the rotation really matters, is the local latitude's orientation relative to that rotation axis, right? So if you're standing at the pole, north or south, you are, as the Earth is spinning, you are spinning perfectly, you are exactly aligned with the rotation axis, right? Whereas if you're at the equator, you're not spinning around like a top. It's more like you're the tip of a fan blade, right? There's a rotation in some sense, but in the horizontal plane, you're effectively non-rotating, right? And so we encapsulate that into the Coriolis parameter. So twice the rotation rate times the sine of latitude. That maximizes at either pole, -1 or +1, and is 0 at the equator. This planetary rotation fundamentally affects large-scale fluid motions, right? And that's from the Coriolis force, right? This apparent force, given that we are in a non-inertial reference frame in that rotating system. So if we start with the horizontal momentum equation for a single layer inviscid non-rotating fluid, we have a UV horizontal velocity vector. We have, in the simplest case, we just have our time derivative, our advection term, and a pressure gradient. That's the non-rotating case. And in the rotating case, that, I'm sure much of this is, for many of you, old hat, but the rotating case, we simply add a cross product of that Coriolis parameter with that horizontal wind vector, right? And the cross product will be at a right angle to the flow itself. What that does is results in steady state geostrophic balance, right? We have, rather than flow from high to low pressure, Coriolis deflects you to right angles, and flow is around isobars instead of perpendicular to them. So that's on any individual level. Now we consider the vertical variation of that geostrophic wind. And that, of course, again, surely familiar, is the thermal wind, right? So we're looking at the vertical shear of, and my particular interest here is of the zonal wind, so du dz. That vertical shear is going to be proportional, it turns out, to inverse of Coriolis times this meridional temperature gradient, dt dy, right? And as we saw in this hypothetical RCE state, of course, this is not 0, right? It's decreasing towards either pole. So let's start with the northern hemisphere and see what signs we get for du dz, this vertical shear. So Coriolis is positive in the northern hemisphere, and dt dy is positive. That's not true. dt dy is negative. I think I missed a minus sign up here and then compensated it for a missed minus sign here. Wow. Oh dear. Sorry about that. Okay, so rest assured, though, nonetheless, if you have the correct minus signs in both places, this part is right. Oh, good Lord. So the point is that du is increasing as you move vertically upward, right? And in the exact same thing holds in the southern hemisphere, where Coriolis is negative, temperature gradient is, oh, okay, that's the only problem. I just flipped this one. And well, no, two things. I flipped this one and the minus sign. This one is right. In both hemispheres, you get a thermal wind shear that is increasing vertically upwards. It was going so well. All right, so wind is increasing upwards, zonal wind. And at the surface, we have the frictional boundary layer, right, where the air is in contact with the hard surface. And so we can say at the lower boundary, no slip. It's a zero zonal wind. So it's 0 at the surface, and it's increasing, becoming more positive upwards, right? And that's happening at all latitudes. So that means throughout the troposphere, at all latitudes in this RCE state, we've got westerly wind. And now we're using this subscript RCE to emphasize that this is this hypothetical location by location RCE state. So we can see that here. So focus just on the blue curves. There's no labels here, sorry, it should be latitude. and then meters per second in the y-axis, just the blue. This is sort of the upper tropospheric zonal wind in that hypothetical, that numerical RCE state I showed you. And indeed, we see this westerlies everywhere, right? Including at the equator. In fact, maximal at the equator. Why does that matter, right? Well, it turns out that that is a state with westerlies everywhere, including all the way to the surface, is a state that cannot be sustained in the time mean. There's a few reasons for that. One involves the maximum occurring at the equator, those westerlies at the equator. But another one that it's a fun one, I think, is that if you have westerly flow, if you have flow in the same direction at all latitudes, right? The wind impinging its stress, the stress imposed on the surface by the wind sort of blowing on it all in the same direction is going to act to spin up the solid body, right? If you have something, spinning on an axis and you keep blowing on it with the same orientation, it's going to spin up, right? So this state would be basically spinning up the Earth's rotation faster and faster and faster, right? Of course, that's not what's happening, right? This is a steady state, not a runaway spun up top or something. So what instead must arise is a mix of easterly winds and westerly winds across the latitudes at the surface, such that the integrated stress over the whole domain is zero, or at least zero in the time mean. How does that happen? A circulation must arise, right? We have this overturning that creates these easterlies in the tropics that we saw at the very beginning and westerlies in the extratropics. Okay, so some circulation has to form, but what controls what that resulting circulation looks like, right? Why does it look like this instead of, say, why don't the Hadley cells go all the way to the poles? Or why isn't it macroturbulent all the way to the equator? So to think about that, let's remember annual mean insolation, highest at the equator, lowest at the poles. And this is very imprecise wording, especially with Marty in the audience, but convection in the atmosphere is, let's put it as, likes where the moist static energy is highest at the surface, right? Heating in a very colloquial sense there, not the latent heating driving the circulation, okay? But anyways, both of those means for sure we're going to expect that convection is occurring most at the equator, less compared to other places. So then why not global Hadley cells, right? Why not this thermally direct circulation where the rising motion is at the equator and we're bringing that energy, that heat all the way to the pole and the return flow at the surface. So now is where we get into the dynamical part. And we'll use angular momentum as the fundamental variable here. Okay, so that's capital M. We have contributions to the angular momentum. So in general, angular momentum is distance from the rotation axis times your linear tangential velocity. And this is strictly speaking angular momentum per unit mass, right? Everything in the atmosphere is we do on this in specific terms. So it's your distance from the rotation axis times how fast you're moving in that direction. Distance from rotation axis on the sphere is simply the radius of the sphere times the cosine of the latitude. And then your tangential velocity is just your zonal velocity u, right? We have two contributions to the angular momentum at any given location. We have the planetary component and we have the relative component. The planetary component is from the Earth spinning itself, right? We have large planetary angular momentum at the equator. We have zero planetary angular momentum at the pole because there's no separation from the rotation axis. And then the relative part is just set by how fast the zonal wind is times the local radius. Okay, again, I've gotten a little ahead of myself. Okay, so now let's picture one of those parcels that left the convecting equatorial band, right? So a parcel there was heated, it rises out of the viscous boundary layer, and it enters into the free troposphere, where, to pretty decent approximation, things are inviscid. The stresses are low, and if you take that all the way to its limit, no friction whatsoever within the free troposphere, then your angular momentum is exactly conserved. So whatever angular momentum a parcel leaves the boundary layer with, it's stuck with it the whole rest of the time it's in the free troposphere. Now we follow that parcel moving forward. It's risen, it's sort of hit its stable layer, and then it starts moving poleward. And as it's doing as it's moving higher latitudes, it is getting closer to the rotation axis, right? Because it's on the sphere. But yet we just said that it's also conserving its angular momentum, right? So the only way that's possible is for the relative flow, the relative contribution to the angular momentum, to speed up in exact proportion to the amount that it's losing planetary angular momentum, right, as it gets closer to the rotation axis. So you can solve very straightforwardly for the angular momentum conserving, or AMC is the acronym you'll see, the angular momentum conserving zonal wind profile given ascent at the equator. That's this expression here, very simple: rotation rate, planetary radius squared, sine squared of latitude over cosine. I encourage you all to work that out. It's like a two-liner. That's what this plot is here. And what I want to bring your attention to is it's sort of this parabolic shape in sine latitude, of course, but also the magnitude, right? So 0 at the equator. And then by the time we're reaching 30 south, 30 north or so, we're something like 100 meters per second. Very fast. And in fact, cosine is the denominator. This blows up as you go to the pole, right? This would be infinite if it extended all the way to either pole. In general, steady states, you can imagine, aren't going to be happy about an infinite zonal wind. And so it turns out that instead the Hadley cells, and with them the sort of upper level wind field associated with them, are only going to extend around to 30 south or north in Earth, at least. And there's two sort of arguments for why that is. One is invoking these purely angular momentum conserving sort of picture, and then a second one that we'll get to right after this. In the inviscid axisymmetric scenario, so meaning everything is perfectly zonally symmetric and steady, we have this idea from Held and Howe 1980 of the equal area model. And what that states is that you have essentially the momentum dynamics are sort of the fundamental part of that model. And if I have time, I'll get back to it later. But it turns out that the way of thinking about the edge of the Hadley cell in this context is in terms of the heat transport. And so what this equal area means is that if you compare the theta sub E here is sort of the forcing, the hypothetical RCE state, if you will, that profile. the angular momentum conserving wind via thermal wind balance gives you instead a theta profile that looks like this solid black line. It's lower than the RCE value in the deep tropics, so it's cooled the deep tropics, and it's higher in the subtropics. It's warmed the subtropics. And insofar as poleward of that, you just have radiative equilibrium. We're ignoring the extratropics entirely. Then you need these two areas to be equal, right? For no net heat transport in the system. So that's a constraint on the extent of the circulation in a purely axisymmetric scenario. But Earth's extratropics, as I've already shown, are surely not in axisymmetric radiative equilibrium, right? It's macroturbulent. We have, here's a nice image over the United States of a textbook baroclinic comma-shaped storm, right? We're going to focus on sort of what these eddies do to the extent of the Hadley cells pretty much the rest of the talk. And then Marty, like I said, will follow up with thinking about their influences on Hadley cell strength. Okay, so to recap all of that so far, we've got a zonal mean insolation gradient, a rapidly rotating spherical planet, a viscous boundary layer, and a quasi-inviscid free troposphere. Those ingredients alone would give us an ITCZ, an ascending branch of the Hadley cells at the equator, and overturning Hadley cells that descend around 30 degrees or so in either hemisphere, and westerlies in the upper troposphere in the tropics. Okay, so now let's talk. I'm going to switch to a different slide deck. And I forgot to say, but same as last time, if you have a question, please don't wait. Are there any right now, in fact? All right. It's perfectly crystal clear. You guys have understood every single word. All right, so I've said all this already, and you saw this yesterday. This is now the actual, from era 5 reanalysis, the actual overturning stream function. And here are our beautiful Hadley cells. We can define, though there's no one unambiguous way of doing it, but we can define a meaningful edge on either end of these cells. So we have this shared ascending edge in the middle, this red phi sub A, I'm calling it, A for ascending. And then our real focus moving forward is these two outer descending edges, phi D for descending. Brief sort of interlude for historical context. One of the reasons I love the Hadley cells is they essentially are what motivated the entire birth of the field back in the 17th century, in fact. Well, maybe we should give the Monsoons even more credit for that. So Halley's paper in 1686 was trying to understand this pattern of easterlies in the tropics, right? And those, of course, are generated by the Hadley cells. I didn't say that part, but if you have westerlies aloft, and then you have sinking motion in the subtropics, and you're then coming back equatorward in your return branch, Coriolis is going to push you the opposite way on the way back, right? Combined with the surface friction that has slowed you down, that actually gives you a net easterly component of your surface wind, just from this simple Hadley circulation. And then Hadley himself sort of was the one that first got much of it right. If you read this, it's remarkable just how much Hadley got right in, what was that, 280 years ago. Then in the 19th century, we had Farrell, who identified the cells of his name in the extratropics. And I would put Heldon Howe as sort of the seminal paper of the 20th century in advancing our understanding. So now let's talk about the migration seasonally of these edges of the cells. So now we're looking month versus latitude. And the shading is stream function, sort of mid-troposphere-ish. And the lines are the edges of those cells. So in red, we have the ascending edge, right? So this dynamical ascending edge has this nice semi-sinusoidal migration. The ITCZ in terms of precip, I don't have it, but it follows this but stays equatorward most of the time. And then in either descending edge also has its own migrations of 10 or 15 degrees or so latitude. It's sort of jumpy in the northern hemisphere and smoother in the southern hemisphere. All right, and okay, so we already covered that. We already covered this. This was a mishmash of a couple different talks, as you might tell. All right, so we have this, we want to account for this macro turbulence, right? The fact that we have this strong eddying regime in the extratropics. And the sort of key breakthrough there, so Isaac maybe gets the seminal paper for the 21st century too, was this work in which the picture is you still keep that angular momentum conserving flow in the throughout the tropics, but then you say that once those winds get fast enough, at least in the two-layer quasi-geostrophic approximation, there's a certain shear created there vertically that becomes baroclinically unstable. And the idea is that the AMC wind keeps going until the latitude at which that instability criterion is met. And then basically the eddies that emerge just sort of, you can think of it as them just sort of like shredding up the cell. It can't go further, it just sort of devolves into these eddies. So this is the schematic. Schematic here is blue is when your AMC, you're still good, and then at some point you get fast enough and a high enough latitude that it's baroclinically unstable, and that's the Hadley cell edge in this model. I asked the organizers, I forget when we started. Okay, great. Okay, so here's a sort of slightly more thorough version of that. So the AMC wind is in orange here, and this blue is this critical wind for baroclinic instability. And the edge is where the orange becomes above or equal to the blue. Okay? I should say this idea of a critical shear for instability is sort of artifactual of this particular two-layer QG thing. More recent work, a seminal sort of literature in the aughts and 2010s from Tapio Schneider's group have tried to sort of use this concept of meridional eddy entropy fluxes to sort of get rid of the QG assumptions and make sort of this all on firmer footing. But the picture doesn't change fundamentally. And this simple QG thing is here's this really simple closed expression for it, right? And that enables us to do further analytical work. So now seasonally, let's consider the AMC solution, but now when the ascent is moving north and south in latitude. So again, here's the ascending edge, its migrations over the calendar year. The orange is the AMC wind when you're at the equator. Here's one way of writing it in the more general case where you allow your ascent to move off equator. And this is a particular example when that ascent is at, say, 20 degrees in either hemisphere. The picture is that you're ascending closer to the rotation axis now, right? And so you have a smaller value of planetary angular momentum that you're stuck with. And so if you go equatorward of there, you're getting farther from the rotation axis. You need to actually become easterly. You need to slow down to keep your angular momentum. And so the difference between these two curves, sort of roughly the span of the ascending edges, actual migrations is something like 50 meters per second. Kang and Liu 2012 were the ones to first capture this. They took this HELD 2000 model and simply well, they did two important things. The first one was just simply accounting for this off-equatorial ascent. All right, so this return of the schematic, this one is the same picture, but now you're off equator, right? So you're off equator, and so now we've got easterlies here. And then once your westerlies pick up, you are less westerly, you're less positive at every latitude. And as such, you can go further before you become baroclinically unstable. And so that means a more poleward extent of the Hadley cell. All right, in the interest of time, I'll skip that. But here's the key problem outstanding to make this realistic for the real atmosphere, is that whether you're in the solstitial regime or in the annual mean, the actual observed zonal winds in the upper troposphere are much slower than the AMC winds. Right, so in the annual, we top out at around maybe 30 meters per second in the subtropical jets, as opposed, 70 something or more meters per second off. Similarly bad both for the easterlies and the westerlies in the solstitial season. We can express that quantitatively using this idea of a local Rossby number. So the local Rossby number is simply minus the relative vorticity over Coriolis, where for this zonal mean perspective here, the minus of relative vorticity is just du dy. All right? I'll just take my word for it, check the math afterwards. The angular momentum conserving state corresponds to this being 1, staying unity at all latitudes. And then this purple is what it actually looks like in the reanalysis for the annual mean. So at most, you're getting 0.4 or so. Even in the solstitial regime, where we get closer to the AMC solution, I want to flag something here. A lot of times in the literature, people talk about the solstitial cross-equatorial cell being the angular momentum conserving case, right? At most, you're getting to 0.7, 0.8 Rossby numbers, right? So we have this sort of, the field has established it's a useful limiting cases of the eddy-driven Rossby equals 0 case and the angular momentum conserving Rossby equals 1 case. But in fact, the system is pretty much always in this sort of murky middle, right? It's sort of undulating seasonally between those two limits, but it's never really in one or the other. Why is it so much slower than the AMC wind? It's because of those eddies, right? The same eddies that are impinging on the edge and forcing it to descend, some of them are propagating further into the tropics. They reach a critical latitude, they break, and they decelerate the winds there. All right. We can encapsulate the effect on the whole cell by averaging this local Rossby number over the whole of each cell. I'm showing that for the northern hemisphere cell in the pink and the southern hemisphere cell in the green as a function of month. And we see this very strong annual cycle in both, right? In the southern hemisphere, we go from about 0.1 or 2 to 0.5 or so. Similarly in the north. And in either cell, it's maximizing in local winter, right? This cross-equatorial solstitial cell is where it's largest. So what we did was simply assume, if we go back to one of these plots of the Rossby number, there is meridional structure, right? Quite a bit, in fact. But let's just assume, what if we just assumed it was uniform? What if we just took the mean value of these curves in either cell, and then what does that give us? Well, what it gives you is a really simple analytical expression for the wind field. It's just the AMC winds times that cell mean Rossby number. Example in the solid for the on-equatorial and off-equatorial case, top and bottom. So you have a decelerated wind compared to the AMC, but almost all of the analytical simplicity. And then when you do that, you do the same ball game of this baroclinic instability criterion to truncate the cells. We have, in a result, In the same way that moving a cent off the equator slows the winds and makes the cell edge poleward, decelerating the winds by reducing the cell mean Rossby number also enables the cell to extend further poleward. All right. I'm going to keep moving. I want to show you some actually results. Okay, so when we assume this fixed Rossby number, do the winds look reasonable at all? In fact, they do. We were pleasantly surprised when I first did this. This was kind of the aha moment. So I'm showing just one example. June, July, August, the actual 200 hectopascal zonal wind in blue. And then in the orange and green are fits within either tropics. We just sort of use this Rossby number as a free parameter and just see what's the best fit we get. And it does a really nice job, right? We then compare that to actually using the diagnosed cell mean Rossby number, right? To make sure we're not like, this isn't something totally arbitrary. And it's nearly as good, right? Yeah. Yeah, great. I'll tip you later. So back to this plot of the cell mean Rossby number as a function of month. The dashed are, the solid is the actual diagnosed, and then the dashed is this best fit version, the one that gives you the best wins, right? And they're basically the same, right? So it's actually that cell mean Rossby number this is physically meaningful is our interpretation. All right, and then here's finally the punchline, the first punchline of this work. We diagnose that cell mean Rossby number for each month, along with the ascending edge, and we compare the prediction of our theory for each hemisphere's descending edge. Southern hemisphere left, northern right, the gray is the actual, and then the blue dots are our theory. And it does a pretty good job, right? Especially in the south. There is this funny thing where we have to lag the northern hemisphere prediction. This is a 1 month lagged, or I forget if it's which direction it is, but and that's something we really don't have an understanding of yet, to be frank. The fun thing is that we have what's showing up in this expression are the ascending edge and the cell mean Rossby number. Those are the two things that can vary. The rest are planetary parameters. And so we can then do a game. Once you have an expression like that, you can say, well, what if I hold one constant? Or what if I hold the other constant? Which one is giving me the behavior of interest? And I'm going quick over the slides, forgive me, but this is what I want you to see. We have those same gray curves and blue dots as before. And now we have two more fields. The red is if we redo this calculation, but we leave the Rossby number at its annual mean value all year round. And you completely lose the southern hemisphere, right? And in the northern hemisphere, it's just in the sort of late fall, boreal fall, that it does okay. Instead, if you leave the ascending edge constant, but you're allowing the Rossby number to vary with season, that's what's controlling the southern hemisphere, and to a large extent, the northern hemisphere as well. In fact, if you just put the ascent just directly at the equator all year round, it still looks pretty much unchanged. So it's the seasonal variations in that cell mean Rossby number, the strength of these eddy stresses, that is predominantly driving the seasonality of the cell, of the descending edge location in either hemisphere. I want to make sure we've got time for questions. We applied this interannually, and there's sort of some nice, not quite as clean as the seasonal cycle, but there's these clear correspondences there as well of interannual migrations of the descending edges and the interannual variations in the cell mean Rossby number. And I really briefly, and we can end with this in fact, want to share that this is sort of, we're appealing to generally applicable arguments to sort of thin shell, rapidly rotating atmospheres, right? Not just Earth. And so as I mentioned in my sort of intro spiel the other day, I have a graduate student, her name's Michelle Wagner at City College, who is using this applied to reanalysis data from Mars. that exists. I learned a few years ago. It's a product called EMARS. In fact, there's like 3 others. And don't stay away. So what I'm showing here is like a mid-tropospheric stream function for Mars. And we have, again, the ascending edges are the solid. Excuse me, the actual diagnosed edges are the solid, so red for ascending and blue for descending. Note, these cells are very different than Earth's in the sense that rather than 2 cells all year round, sort of undulating in size, you have this abrupt and sort of all 1-cell regime where the sort of winter cross-equatorial cell just takes over the whole tropics. And then it's a very rapid migration to the other one. The dots are theories, the blue dots are theory using that time-varying ascending edge and Rossby number to try to capture the descending edges. And it's not perfect by any means. It's not as good as for Earth, but in both hemispheres, you capture some of the behavior, right? And actually, the behavior is opposite in the 2 hemispheres, right? So for this northern cell, it sort of starts low and then maximizes, then goes back down. The southern cell, it sort of starts poleward most and then goes back and then poleward again. And in both cases, the theory is getting you at least that broad picture. Okay, so I think I'll leave it there. So I think the thing to emphasize is to understand the Hadley cell, why the Hadley cells exist. The RCE state, the state if there was no circulation, is just, it's unstable. It just can't persist for any number of regions. And then to understand the extent of the Hadley cell and how it varies with season, and to some extent interannually, we need to understand how it is being influenced by this macro turbulence, right? So what happens in the extratropics doesn't stay in the extratropics, right? We have equatorward propagation, stresses imparted on the Hadley cells, and those are sort of, I think, fundamental to understanding the observed seasonal cycle. Okay, thank you.
Questions? Thank you, Spencer, for a very nice talk. I wanted to know why the ascending branch of Hadley cell is stronger, narrower, and the descending branch is broader and weaker. What are your thoughts about that? Maybe you covered this, I missed.
I didn't.
Okay.
Yeah, great question. It's, in a word, it's moisture, right? So it's the latent heating, sort of, very crudely speaking, sort of enables the cell, the ascending branch, to contract and intensify. So in a dry atmosphere, you actually have exactly equal areas of your, not in the Held-Howe sense, equal extents of the ascending and descending branches. And that reminds me, I think I forgot to mention in the successes thing yesterday about the ITCZ, is this whole framework of the ITCZ width. So this is spearheaded by Mike Byrne at University of St. Andrews, among others. And what they've done is they're trying to understand what controls the width of that ascending branch of the ITCZ. And their starting place was the same energetic framework that was originally for shifts. Yeah.
Thanks, Spencer, for the great talk. I have a bit of a naive question. So you mentioned that you consider the cell mean Rossby number. Do you, yeah, is it better now? Yeah, okay. So you mentioned that you consider cell mean Rossby number. Do you need the extent of the cell to compute the cell mean?
That's a very good question. It's circular, right? We're averaging over the extent of the descending branch, and then using that to predict the extent of the descending edge. Yeah. So Michelle, my student, to her credit, raised this in the context of the Martian, applying it to Mars. And so then we went back, and so then I kind of panicked for a second, because that's obvious, but it never fully clicked with me. And so then we went back and she did the Martian calculations just using a fixed latitude range. And I went back and did it for Earth, and it still holds. Yeah, if you just use a fixed latitude range, you still get the same broad seasonal migrations. So this is not just an artifact of the further you go the further the cell goes poleward, the more the Rossby number decreases. Yeah.
In that context, I mean, we know the extent kind of depends on the rotation rate, right? So
Absolutely, yeah.
if you consider like a very slow rotating planet, then does the fix that you did, does that break?
So I showed Titan, right? Remember yesterday, this ITCZ that goes pole to pole? We tried applying this to Titan to see if it would, you know, if the descending edge, if there was some variation in the descending edges there. It's too messy, that planetary atmosphere. There's too much weird stuff going on. But in the context of just idealized models where we just reduce the rotation rate, yeah, we do see it broadly works. I haven't done a ton in that regard, but yeah, and even you can see for Mars. So Mars is nearly the same rotation rate as Earth, but it's smaller radius, right? And the key parameter for the Hadley cell extent is the thermal Rossby number, which is gravity, sort of height of the troposphere, as it were, and a meridional temperature gradient of the forcing, and then rotation rate radius squared. And so the rotation and the radius do the exact same thing. So a smaller radius is the same as the smaller rotation rate. And so you can see, right, the Hadley cell edges on Mars are 40, 50, sometimes beyond 50 degrees latitude.
Thank you.
Spencer, actually, I have a small kind of clarificatory question. So we think of Rossby number, local Rossby number. So we are essentially considering how big is relative vorticity as compared to the local planetary rotation. And Rossby numbers as high as, I think, in your plot of what Rossby number, local Rossby number gives you the best fit. Yeah, so it goes until 0.5. Does it say anything about if are there any constraints on how far it can go from theory or?
Yeah, so it's a great question. A key limitation of this whole framework is that we are just diagnosing the Rossby number. Even if you set aside the potential circularity, right? I don't have a theory for this cell mean Rossby number that's predictive, right? That's in fact something that is sort of my white whale for the next N years. Well, hopefully it's not literally my white whale. Hopefully it doesn't kill me, but but like that's what we're going for. But I think it's a really hard problem. You could think of it sort of as the ascending branch and the descending branch being controlled by different factors. For the ascending branch, there's this really interesting work. My current thinking is there's this really interesting work from Brian Hoskins and Yang over the last few years, where it's about the spatiotemporal frequency of convection. The idea being the Rossby 1 case requires that you're sort of constantly at all longitudes advecting that planetary angular momentum into the free troposphere. If you weren't, then because when you're quiescent, there's no transport, and so the time mean will be brought down by any places and times where it's not convecting. But then it turns into a theory for that spatiotemporal occurrence of convection, which sounds hard. Some of you in this room would be better posed to do that than I would. For the descending branch, what we're thinking is maybe this framework called Rossby wave chromatography. David Lorenz, not Ed Lorenz, has these papers that are really dense, but really interesting, where the idea is that you account for the different critical latitude location and thus where the wave breaking is happening as a function of the wave number of and phase speed of of the eddies, because there's the breaking latitude is a phase number, a phase speed dependent quantity. But that's like, all of that is just, we haven't really even gotten started at all. So yeah, so just like yesterday, I'll say, you all should do that. You all should come to the next monsoon meeting and solve that. The difference from the yesterday is that, like, for this one, like, I'm racing you there.
A good one. So maybe a follow-up comment would be, in last week, we heard Divya and Rajat show some low-level dynamics, low-level flows. And they were making a case for high Rossby number at lower levels.
Yeah.
And that puzzles me even further. Any thoughts on that?
No, I regret that I couldn't be there. I'm excited to hear more about that work. Yeah, and it was sort of not my intuition. My intuition would have been, there's friction in the boundary in the boundary layer. There's that's going to be even less capable of getting to this sort of zero absolute vorticity region. But that's probably just my ignorance about boundary layer processes more than anything. So it's exciting work. And that reminds me, actually, on Heladames, I don't know if Victor's on it as well, but they have a manuscript. There's a preprint out for sure, maybe it's been published now, where they are actually doing sort of from this moisture mode Hadley cell interaction arguments, they're coming up with some theoretical expression for the near surface boundary layer Rossby number. So that's also, I haven't sort of thought deeply about that, but that's an exciting front, I think. Too.
Like moist Rossby number in some sense.
Yeah, yeah. Well, it's all moist, right? It's all.
Yeah. Yeah, happy to introduce Professor Debashish Sengupta. Few people have asked me who was that professor who showed up that day. So very happy to introduce Professor Sengupta.
I'm more happy to be attending these. Thank you, Spencer. And is it possible to think of an atmosphere where this vertical shear is so large that the atmosphere gets mixed up?
Yeah, so in fact, you can think of this baroclinic instability in some ways as operating once the vertical shear does get unstable, right? So we have, you can think of that as sort of orthogonal to barotropic instability, where it's the horizontal shear that reaches a critical amount and then it sort of sheds into eddies or becomes unstable. The baroclinic instability, which is driven by the meridional temperature gradients, because through this thermal wind balance, the meridional gradient is what sets the vertical shear. When you're rotating fast, depending on the rotation rate, you need more or less shear, but once you reach that critical, again, in the simple QG case, you could think of it as a critical shear arises and then these eddies emerge.
I guess what I meant is enough to completely erase the stratification.
Oh, like,
Just the entire thing is a boundary layer.
That's a pretty exotic regime. I don't know if anybody else has any intuition there. That's a fun question, but in any scenario that people look at that I'm familiar with, you have, as soon as you get out of the boundary layer, no matter how deep it gets, it's at most a third or so of the overall depth of the troposphere, and then you're very rapidly into a fairly inviscid environment, less these eddy stresses.
Yeah, thank you.
Finite equivalent depth regime or something like that.
Someone should make a simulation that generates that state. That would be fun.
Yeah. If there are no kind of further questions, let's thank Spencer once again for a very nice talk.